This video lecture has to do with a nucleus. What do we know about a nucleus? Well, inside the nucleus there are neutrons and protons. Collectively they're known as nucleons. Any given element in the universe comes in a variety of forms. They all have the same number of protons, but they have varying number of neutrons. Those different varieties of that element are called isotopes. Let's look at a particular isotope of carbon, and this is how it's symbolized. Subscript 6 indicates the number of protons in this case, but more generally it represents the charge, the total charge of the nucleus as a multiple of the proton charge E. The superscript represents the number of nucleons, in this case 12. So there's 6 protons and 6 neutrons. The sum of the two numbers is 12. And the nucleus's attempt to become more stable, it will emit either energy in the form of electromagnetic energy or one or more particles. And there are different modes of decay, as we call it, different modes by which the nucleus becomes more stable. Carbon-14, so named because there's 14 nucleons in that version, that isotope of carbon, decays by means of a beta particle emission. A beta particle, so called because it's the second letter of the alphabet. It was the second of 2 unknown types of particles emitted during radioactive decay. The first particle was called the alpha particle, later discovered its actual form. And then there's the beta particle. The beta particle turned out later to be just an electron. So there are 2 names that you can attach to the beta particle, either call it an electron or a beta particle. In this case, notice that the carbon-14 nucleus is replaced by a nitrogen-14 nucleus, and flying away at great speed from that location is an electron. Notice further that the superscripts add up on either side of the time arrow, 14 on the left, 14 plus 0 on the right, and the subscripts likewise add up on the left and right side, 6 on the left, 7 and a negative 1, 6 on the right. There's a second mode of radioactive decay, and it's called alpha decay. An alpha particle is a clump of nucleons, 2 protons and 2 neutrons, and it's symbolized this way. Subscript 2, meaning its total charge is twice the charge of a proton, 2 times E, and a superscript indicates that there are 4 nucleons in this thing, 2 protons and 2 neutrons. Radon-222, atomic number 86 on the periodic table, decays by means of alpha particle emission. After time goes by, assume the length of time, an alpha particle is emitted from this nucleus, and what's left behind is a polonium-218 nucleus. Notice, as before, the equation is balanced, so-called balanced top and bottom. On the left is 222 superscript, on the right is 218 plus 4 is 222, that's good. On the bottom, 86 on the left, 84 plus 2 on the right. This decay equation is balanced in the same manner as is achieved when one is, quote, balancing chemical reaction equations. The third most common type of radioactive decay mode or method is a gamma decay. That happens when a photon, one or more actually, a photon is emitted from the nucleus, and usually what happens is that there is another particle, a particle emitted simultaneously. That's the case for iodine-131. It decays by means of beta particle emission alongside of a photon being liberated. And notice once again the subscripts add up, 53 on the left, 54 and negative 1, and on the top 131, 131. That symbol there is a symbol for a photon. That's the Greek letter gamma. Notice that its charge is 0, and it's not a nucleon because it's not a proton, it's not a neutron, so there's a 0 there. Now, how long does it take, for example, for this decay to occur? Over a period of seconds, months, weeks, days, minutes, what? Same question we could ask about this. Well, this calls for a discussion of a thing called half-life. The half-life is a period of time. It could be conveniently measured in microseconds, seconds, minutes, hours, days, months, years. millennia, centuries. The half-life of a substance, of an isotope, is the average amount of time it takes for half of the radioactive sample to decay, to disappear, to become something else. Let's look at iodine-131, whose half-life is known to be about 8 days. This table shows the progression of loss of iodine-131 nuclei. At day 0, we have capital M, the mass in micrograms of iodine-131 present, 240. After 8 days, half of that. 8 more days, for a total of 16, half of the 120, half of the 60, and so on to 15, and 7.5, and 3.75, and so on, and so on, and so on. A graph of these numbers, M measured in micrograms versus time measured in days, is an exponentially decaying graph whose equation is given by this, whose equation is this. M naught is the amount of mass present at time 0, in this case 240. T is the amount of days that have gone by, and lambda is the so-called decay constant. We'll discuss the decay constant and work some problems involving half-life in our next lecture. I hope you learned something. For now, I'll say goodbye. Have a good day.